Today I'm going to give you a comprehensive revision of Physics 2018, Paper 1. This is a paper that was done 4 years ago, and we're going to look section 1 of it. So let us jump into the first question. The first question reads, state the reasons why an object on Earth has a higher weight than an object on the Moon. Now let us look at the basic foundation of how we are going to handle this question. The weight of an object is determined by the force of gravity acting on it. Earth has a higher gravitational pull than the Moon, resulting in a greater force and consequently a higher weight on Earth. Therefore, the simplest answer to this question is that the Earth's gravity is higher than the Moon's gravity. Remember, it's not the mass that changes, because mass involves the amount of substance in an object and does not change in any position. It is the region's gravity that determines the weight of an object. Therefore, the gravity of the Earth, because the Earth has a higher gravity than the Moon, the object has a higher weight on Earth than the Moon. The second question reads, the figure 1 below shows the position of a student's eye while measuring the length of a wooden block using a meter rule. So this is a Form 1 work, measurement 1. When you are taking readings from a meter rule, in fact, it's testing you to look at the precautions to use while measuring the lengths. So the first one is to ensure that the zero mark aligns precisely. The zero mark should be at the beginning of the object. However, in the diagram you see the object is starting at 6 mark, but therefore it should be precise. Also, you should read the measurement at the point where the object ends. So your object, you should read the reading perpendicular to where the object ends. That should be the reading of the meter rule. Also, you should consider parallax by viewing the measurement straight for accuracy. So parallax involves viewing. For example, if we look at this ice student, this is parallax. It is going to give incorrect measurement because it is not straight from this point to where the object ends. Therefore, the correct way to make the reading is to view this object from the top, perpendicular to where the meter rule is. And this one, following all these rules, we get the reading as 7.3 is where the object ends, and the initial position was not 0, it was 6.0. Therefore, if we subtract 6.0 from 7.3, we get 1.3 centimeters. So that is the reading of that object. So the object measures 1.3 centimeters. The next question, describe how the knowledge of the oil drop experiment may be used to estimate the area of oil spillage from a ship in the sea, assuming the surface water is not disturbed. This is oil drop experiment Form 2 work, and in this experiment, and in the oil drop experiment analog, you can measure a known volume of spilled oil by observing it spread on the controlled water sample and then estimate the area it covers. Applying this to a real scenario, you measure the spilled oil spread on the sea to estimate the total area affected. Then this method leverages the oil drop experiment principles for practical estimation of the extent of an oil spill on a larger scale. Now the simple answer to this question is that you use the oil spilled to measure a known volume. You use the exact oil that is spilled on the sea and measure a known volume. That is the one that we'll be using to estimate. Then the next one is to determine the area or spread of the measured volume on the water sample. So you pick the water sample from the sea and drop that oil with a measured volume and measure the area at which that volume of the oil spread. Then the last one is to estimate the area spread on the sea. So using that analog, you can easily estimate the area of the oil spilled. The next question reads, the figure 2 shows an instrument used to measure atmospheric pressure. You can see, if you can see the meniscus, you can easily realize that the substance or the liquid substance is mercury, because mercury is the only liquid that has its meniscus curving downwards. So state with a reason the modification that could be required in a similar setup if mercury were replaced with water. So if mercury is replaced with water in an atmospheric pressure measurement instrument, the tube could need to be significantly longer due to water's lower density compared to mercury. Remember, mercury has a density of 13.6 grams per cubic centimeters, and water has a density of 1 gram per cubic centimeters. Therefore, there is a difference in those densities. That's why we may need a tube of longer length. Mercury is about 13.6 times denser than water. To maintain the same pressure sensitivity, a longer water column compensates for its lower density, ensuring the instrument accurately reflects atmospheric pressure changes. Therefore, the simple answer to this question is that the tube will be very long, since water has much lower density than mercury. The next question reads, it is observed that a drop of milk carefully put in a cup of water turns the water white after some time. State the reason for this observation. This is a Form 1 work, particulate nature of matter, and here we are testing a property known as diffusion, where we have particles in a concentrated area moving to regions where concentration is low. So milk particles move to occupy the spaces where the water particles move to occupy the spaces between the water particles through diffusion. Diffusion is the process by which particles move from a higher concentrated region to a lower concentrated region. There is an error here, to a lower concentrated region. So this process is responsible for milk particles spreading throughout water in the cup. So if you have a drop of milk, that drop is highly concentrated with milk particles. If you place in water, water has low concentration of milk particles. Therefore, the milk particles will move from their concentrated region and spread throughout the cup. Question 6 reads, Figure 3 shows the sample of a bimetallic strip after it was cooled below room temperature. So you have a bimetallic strip. This one comes from linear expansion, Form 1 work, and we have two types of substances. We have INVA and brass. So these substances are combined together, and you can see brass has a shorter length than INVA. So this is after cooling. So explain why the strip curved as shown. So the strip curved because of a difference in linear expansivities. Therefore, the reason to this question is that brass contracts more than INVA, hence contracts leaving the side with INVA, hence the curve. Brass contracts more than INVA because brass has a higher coefficient of linear expansion. When a substance has a higher coefficient of linear expansion, it contracts and expands more than a substance that has a lower coefficient of linear expansion. Therefore, INVA with its lower coefficient exhibits less dimensional change in response to temperature variations. The next question reads, a wooden cube of side 0.5 meters floats in water, fully submerged. Determine the weight of the cube given that the density of water is 1 gram per cubic centimeter. This one comes from Form 4 work under floating and sinking. Now the first thing we look at is that this cube measures 0.5 meters, meaning all the sides are equal, and a cube is such a way that all sides are equal. And this question comes from the law, the flotation, floating and sinking, and it is based on the law of flotation, which states that the object displaces its own weight. Now we are asked to determine the weight of the cube. So if it is fully submerged, it means that this cube displaces water of the same weight as the cube. So in this case, we are going to look at the volume of water displaced, and the volume of water displaced will be equal to the volume of the cube, which is 0.5 meters times 0.5 meters times 0.5 meters, and you get 0.125 cubic meters. This is the volume of the cube, and it's the same volume that this cube displaces. Therefore, the volume of the water displaced is 0.125 cubic meters. The next thing we want to look at is the weight of the wooden cube, which is the weight of the water displaced. So that is the volume of water displaced. So the weight of the wooden cube will be equal to the same as the weight of water displaced, and the weight of the water displaced is given by volume of water displaced times the density times gravity. The density of water is 1 gram per cubic centimeters. If we convert to the SI units, we get 1,000 kilograms per cubic meter. And if we substitute all those in the formula, we get it is 0.125 cubic centimeters times cubic meters. There is an error here. It is supposed to be cubic meters. You multiply by 1,000 kilograms per cubic meter. You multiply by 10 newtons per kg. 10 newtons per kg is the gravity on the earth, and this one will give you as 1250 newtons. 1250 newtons is the weight of the water displaced, and following Archimedes' principle, the weight of the water displaced is equal to the weight of the object that displaced that water. Therefore, the weight of the cube is 1250 newtons. The buoyant force exerted by water on fully submerged wooden block is equal to the weight of water displaced. The buoyant force is given by the formula, the same formula we discussed, which is density times volume times gravity, where rho is the density of water, v is the volume of the block, and the g is the acceleration due to gravity on earth. And using these values, we find the weight of the wooden block to be 1250 newtons. The next question reads, the figure 4 below shows a stone wheeled in a vertical circle. This one comes from circular motion. Under the circular motion, we are going to focus mostly on tensional force. So you have a stone and you wheel it. This is assumed this is the hand, and you wheel it in a circular path. Remember, there are two types of velocities. We have the angular velocity and the linear velocity. The angular velocity is the one that is keeping this stone to move in a circular path. So the angular velocity together with the tensional force are the ones that are responsible for keeping this stone in a circular path. So on the axis provided, sketch a graph of tensional against time as the stone moves through the point A, B, C, and D. The stone is moving from one point to another. D is at the top, B is at the bottom, and A and C are at the sideways. So there are a number of phenomena that happen at these specific points. And before we draw a graph, let us look at those types of phenomena that takes place at those points. So when the stone is at the bottom, point B, the tension is at its maximum as it counteracts gravity. At this point, we have maximum tension. At the top, point D, the tension is at its minimum since it supplements gravity. So this is at the top here. We have the lowest tension. At the bottom, we have the highest tension of force. But at the sideways, the tension at points A and C, tension varies between these extremes. So we have the same type of tension. In this case, we will plot a graph reflecting these changes with the highest point corresponding to D and the lowest point corresponding to B. So this is the graph. So these are the points. The highest point, this is the highest point. This is where D is. This is where B is. This is where A is, and this is where D is. So the y-axis is the tension that is experienced by this string, and the lowest and the x-axis is the time it takes to move from one point to another. So the answer to this question is just the plot of this graph, and it was just a rough plot. It was not based on specific values. The next question reads, the figure below shows a ball spinning as it moves. This question comes from Bernoulli effect in form 2, and we have a ball that is spinning while moving forward. This is the initial path, but you are seeing the ball moving upwards. So point A, on the diagram, sketch the path followed by the ball as it moves. The second one is explain why the ball takes that path. So this is how the ball moves. You can see the ball is curving upwards. So the path of the ball curves upwards. I'm going to give you an explanation. The ball takes the path represented in the diagram because of the Bernoulli effect caused by the difference in air pressure due to streamlines. So the air pressure, there is a change in pressure. On the top here we have the lowest pressure because here on the top we have the highest velocity compared to the bottom part. So there is a change, there is differences in pressure. Therefore, the path curves upwards. As the ball moves to the right, the airstream moves to the left. Spin is anti-clockwise. A region of low pressure forms above lifting the ball. So this is the low pressure, the region of low pressure that is formed that lifts the ball upwards. Also, the rotation of the ball creates a pressure difference on opposite sides of the ball, causing it to curve. This aerodynamic phenomena coupled with the Bernoulli effect results in a dynamic lift force. As the ball follows its path, the combination of these effects influences its trajectory, showcasing the intricate interplay between airflow, spin, and pressure differentials. The 10th question reads, Figure 6 shows the relationship between volume and the pressure for a certain gas. So this one comes from gas laws. We have, as you can see, we are comparing volume to pressure. So this is Boyle's law, where we have a relationship between volume and pressure. So the gas law being tested is Boyle's law. This is Boyle's one. As you can see, this one is 1 divided by pressure. When you do a reciprocal, the graph becomes a straight line passing through the origin. However, if we have 1 pressure here, we'll be having a graph that is coming from upwards here downwards to this point, and this one shows the inverse relationship between volume and the pressure. So Boyle's law states that at constant temperature, the pressure of a given amount of gas is inversely proportional to its volume. Mathematically, this can be expressed as P1 V1. P1 is the first pressure and V1 is the first volume, will be equal to a constant, and the second pressure and the second volume will be equal to a constant, and because the constants are the same, P1 V1 will be equal to P2 V2. V is the volume, and the subscripts 1 and 2 denote the initial and final states respectively. This law describes the relationship between pressure and volume in a closed system where temperature remains constant. So question 11 reads, Figure 7 below shows the L-shaped gooden structure. So this is the structure. You can see it has 2 rectangles, the horizontal one and the vertical one. So on the diagram, construct appropriate lines to show the position of the center of gravity for the structure. So we are going to draw this. So for our revision, I'm going to redraw again this structure, and I'm going to show you a step-by-step way of determining the center of gravity. So the first one, we draw the vertical rectangle like that, and also we draw the horizontal structure like that. So you can see it's the same. This one is the same. So what we do is that we are going to draw the diagonals. We're going to construct the diagonals and find the central point of this vertical rectangle. So the first diagonal is that one. So make sure you touch the points, the specific points like that. The second diagonal, I've used different colors so that you can easily see the central points. This is the first central point of this vertical rectangle. So if it was this rectangle alone, the center of gravity will be at this point. But because there are two, let us also determine the center of gravity of this horizontal rectangle. We make a diagonal on that rectangle, and also we make the second rectangle, and the point where they intersect is where its center of gravity is. Now how can we now determine the center of gravity of the both of the two structures, because the two of the structures are combined, and we have to determine the position where the center of gravity acts. Now the first thing is that we draw a line that connects this point here and where this point is, a very straight line. Then the next we're going to draw a line that joins the two centers of gravities for every rectangle. So we are going to draw a line that joins this center of gravity, the horizontal one, and the vertical center of gravity like that. So where these two meets is where the center of gravity is acting. As you can see, the center of gravity is acting outside. It is acting outside the structure. So point X is the middle point of the intersection of the two lines, and it's where the center of gravity for the whole structure acts. So X is the position of the center of gravity. Question 12 reads, the figure below shows the graph of extension against force for a certain helical spring. So we have this comes from Hooke's law from 2 work, where you have springs. We have so many applications of springs. So and a spring is used to absorb shock in vehicles, motorbikes, among others. So here we have a graph of two variables, that is the force, that is the extension against the force, and on the same diagram we are supposed to sketch the graph of extension against force for a spring with a lower value of spring constant. So that is how we draw the graph. We are going to start to draw the graph. So we have the vertical axis, that is where extension is, extension in centimeters. We have the horizontal axis, that is where the force is, and the force is measured in newtons. And that is the original line, that is the original relationship before you were asked the question. Now, before we answer this question, let us look at this. When the spring constant decreases, the extension force graph typically exhibits changes. A lower spring constant indicates that the spring becomes less stiff, and when the spring becomes less stiff, extension increases. As a result, for a given applied force, the extension of the spring will be greater compared to a stiffer spring. This relationship is reflected in the graph as a shallower slope, indicating that it takes more displacement to achieve the same force. So in this our graph, the extension against force for a spring with a lower value of spring constant, if plotted, becomes like that. So that is the correct one. Question 13 reads, state 2 ways in which a mercury-based thermometer can be modified to read very small temperatures. We have a mercury thermometer. How can it be modified to read very small temperature changes? These are the answers. To enhance the sensitivity of a mercury thermometer to detect very small temperature changes, you can consider the following modifications. One of the modification is making the bulb thinner. Remember, mercury thermometer is using a bulb, so you make the bulb thinner so that it can be able to record, to be sensitive to small temperature changes. The next one is making the bore narrower. The above mentioned modifications aim to make the thermometer more sensitive to minute temperature fluctuations, enabling it to register very small changes more accurately.